Okay, so it is 12, so let us start. Let me share my Okay, so what I do today is, yeah, last Friday I said that maybe we'll do FFT at the end, but let me not do that. Let me finish FFT discussion. It will take maybe 20 minutes or so. Okay, I mean, let's not leave it hanging like that. Yeah, because it is an important topic. Okay, so yeah, and since we discussed half of it last time, let us finish that, and then after that we can start with the Laplace transform. Okay, so that is the plan today. We will finish SFT. Some of you might have gone through yeah, this material already. So yeah, many of you might be already familiar with what is going to come. Okay, but yeah, for those who have any doubts or yeah, if anything is not clear, let's finish this off maybe in 20 minutes or so, and then yeah, we can start with the Laplace transform. So yeah, the plan after the Laplace transform is maybe I will come back to sampling and Z transform. We will keep it at the end. Okay, so yeah, we may not get enough time to discuss whole of Z transform, but if you understand Laplace transform and Fourier transform, then yeah, understanding Z transform is does not require too much of an effort. Okay, just getting familiar with some notations and so. Okay. So that is the plan. We will start with Laplace transform, and we might not. I mean, yeah, I don't think we will finish it this week, but yeah, some point next week we will finish Laplace transform, and after that we will start with sampling and filter, and little bit of systems also. All right. So back to today's discussion. Yeah, so before that, yeah, there were a couple of mistakes I made, not very big mistakes, but yeah, let me correct those. Okay, just give me a moment. I'm unable to select this. He has got hand or just give me a moment. Okay, so by the time this gets open, yeah, let me do correction in the okay, it is here. Yeah. So while doing this Gaussian function and its Fourier transform. While doing its inverse, I said that G0 comes directly from this expression, which is not true. Okay, this is something which we are trying to find. We don't know what G of t is. We are only given G of j omega, and from that we are trying to find what is G of t. Okay, so this is our unknown G of 0, and yeah, we cannot just plug in uh, G of 0 from here because we don't know what G of t is. Yeah. So g of t is g of 0 times this exponential. And how to get this g of 0 is by using this. Okay, so g of t, this is by inverse Fourier transform. And to find g of 0, you just put t is equal to 0 here and you do this integral. Okay, so if you do this integral from minus infinity to infinity, you do get this term 1 over sigma root 2 pi, which is the area under this Gaussian curve. So that's where this G of 0 comes from, not from this. That was one thing which I said incorrectly. And the other one is, yeah, I also said that if we have a matrix times a vector multiplication. So if this is a Fourier matrix, which is a 1000 cross 1000, not write that. Okay, 10 to the power 3 cross 10. So yeah, if you do usual matrix vector multiplication, then that requires 1 million computations, which is 10 to the power 3 squared. And if you do fast Fourier transform, then it requires 10 to the power 3 times. So this is not log to the base 10, this is log to the base 2. Log to the base 2. So last time I did log to the power 10. That's why we said that, I said that this is 3k, which is not true. This is 10k, which is still significantly cheaper compared to 1 million. So log to the base 2 of 1000 is 10 approximately. Okay, so instead of 3 you have 10 factors. Yeah, those were the two corrections. Alright, so that n log n, log is to the base 2. So that is to the keeping. Alright, so let us continue FFT. Yeah. Any questions? Alright, so we also saw this trick last time of yeah. Okay, please be on mute. Okay, otherwise, yeah, I feel like there is a question and yeah, it causes disturbance. Yeah, so you can use this trick of using a permutation matrix. So f times x is same as f times p transpose times x. This is identity because this is a permutation matrix. So when you post multiply f by p, you permute columns of f, and here you permute rows of x. Okay, so that's what we are doing in here. We are permuting columns of f, columns of f, and we are permuting rows of x. Okay, so this is the permutation of rows of x, and yeah. So thing to notice in this Fourier matrix of size 8 cross 8 is the following. So once you permute these columns, this first 4 cross 4 block, that you can identify with F4 matrix. Okay, so omega is 8th root of unity. So omega to the power 8 is 1. So this is yeah, you can write a complex expression for omega. So omega to the power 2. This is 4th root of unity. And further simplification, this first 4 cross 4 block, that actually forms yeah, this, Fourier matrix of order 4. Okay, this bottom block, so lower block is also the same matrix. What we have here is some multiple of the Fourier matrix. So this omega 4, capital omega 4, this is a diagonal matrix. Okay, like this. So diag of 1, omega 8 squared, and omega 8 cubed. Okay, omega 8 is the 8th root of unity, and this capital omega 4 is this diagonal matrix. Okay, so this permuted matrix we can write in this block form. Okay, where yeah, you know all these entries, and this x vector we have divided into two parts now: odd components and even components. Okay, so first 4 blocks form odd indices, and the last 4 blocks form even indices. Okay, so let's do further simplification. This we can rewrite as okay, so f4 you take it to this side. Yeah, so f4 times the first block and f4 times the lower block, and yeah, these two expressions are the same. You can verify that, okay, just by simple matrix algebra. Okay, so now how to compute this DFT of let's call this 8-point DFT, okay, because we have 8 points in our DFT. yeah, so we want to find 8-point DFT. So our input vector is of size 8 cross 1 and its DFT is also of size 8 cross 1. So how we are going to do that? We are going to use 4-point DFT yeah, to compute the 8-point DFT. And then we are going to apply recursion to this 4-point DFTs and so on until we can uh, divide no further. Okay. So let's understand this these two lines of the code. So y vector is this f8 times x. This we are calling the DFT vector of vector x. So first 4 entries you can see from here. Uh, so y of t is just f4 times yeah, this first block. Okay. So this block we are called. This is our first block vector yeah, from here that we are calling y of t. This second block vector we are calling y of t. Okay, so this is y of t, the top one, bottom one is y of t, and this is just vec of this diagonal matrix. Okay, so the diagonal entries of this matrix you put it in a vector like that. Okay, so omega is same as omega 8. Yeah, and this is entry-wise multiplication. Okay, so whether you have a diagonal matrix multiplying this, or you have a vector where you are doing entry-wise multiplication, it is the same. Yeah. So omega 4 times this is same as doing this entry by entry multiplication using vector. Yeah. So the top block of y vector, that is just y of t, which is this part times identity plus this omega 4 times the lower block. Okay, so these this line gives you the top 4 entries, and likewise this gives you the bottom 4 entries. Okay. So that's the algorithm to go from 8 cross 8 to 4 cross 4 and cross 4 to 2 cross 2 like that. Okay. So this is the FT algorithm, which is pretty easy and compact. Okay. So suppose you have your n is some power of, so yeah, if n is equal to 1, your Fourier transform is just your given entry. So for scalars, yeah, Fourier transform is the same. So this is the base case, and now yeah, now we are going to recurse on the base case. So in the first step, we are going to divide our vector into two blocks of size n over 2. Okay, so yeah, you divide your vector into two components of size n over 2, which is m. So you find the FFT, so you call your function, yeah, and find the Fourier transform of the top component, find the Fourier transform of the lower component. So yeah, this you do recursively for each m. So after that you form this V vector using your roots of unity. So up to omega to the power of m minus 1 you have to do at each step of this loop. Okay. Then yeah, Z is just this product, and here you combine your solution. Okay, so this is the merge step, this is divide. So yeah, this is divide and conquer step, and this is the merge step here, where you put up your solutions together. Okay. And yeah, this will go on recursively. So for n over 2, when you call this function again, you are going to divide again, and yeah, like that you are going to recurse on that. Okay, so I hope this algorithm is clear to all of you. If there are any questions, yeah, feel free to ask. Okay, so you can give it a thought, and yeah, you can ask questions whenever you want. So let us try to understand the complexity. Okay, so I'm just going to give one way to understand this. Of course, computer scientists can do much better than what I am going to do. And yeah, many of you guys might be already knowing better way is of showing this complexity. Okay, yeah, I'm just going to give one possible explanation. If anyone yeah has any ideas, then you can go ahead and yeah, feel free to express yourself. Okay, so let's try to understand this complexity, why it is n log n. If you don't get hang of this, that's also fine. But, yeah, let me give let me explain this once actually. Okay, so let us try to understand where are our complexities. So at this step we are doing recursion. So this is going to go into the loop recursively. At this step we are doing order n computation. Okay, because there are yeah, n by 2 blocks in here and n by 2 blocks in here, and yeah, there are order n additions and subtraction now. Okay, so this line comes from this step and this step. So order n is here. Yeah, when uh, you call this function for the first time, there are order n operations in the merge step, and there are so yeah, Fn is the total number of computation required for to execute this FFT algorithm, and since you are calling this twice, yeah, in the first call, there are two Fm number of computations. Okay, so Fm here once and Fm here once. Okay, so that's from that is where this 2 Fm comes from. Okay, uh, this is again order m and order m sort of. So yeah, that gets consumed in order m. So I hope this step is fine with everyone. So order n we have here, which is coming from this side. So yeah, we cannot simplify this any further. Now let's expand this f sub m. Okay, so we have 2 outside, and fm is again 2 times fm over 2 and order m. Okay, by the same logic. Okay, and this is going to go on, yeah, until you hit 1. Okay, and yeah, the argument I'm going to give is yeah, this sum is order n added n log n, sorry, order n added log n time. So n is some power of 2, so n is log to the power of t. So yeah, this you can uh, simplify log t time. So let me explain that a little bit better. Yeah, so we have 2 times 2 f m over 2 plus order m. Yeah, this is order n. Okay, so if I expand this out, I'm going to get 2 squared here, f of m over 2 plus twice order n over 2, because yeah, this m is n over 2. Okay, and this is same as order n. Okay, so that you can see it from here also. So yeah, in this merge step, yeah, there are order n over 2 scalar operations here and order n over 2 scalar operations here, but yeah, you are doing them twice. Yeah, so this complexity is still order n, and that is the same explanation behind this also, why this is same as order n. Okay, so we have one more order n coming from here. There was this order n from the first step, then another order n from the second call, and yeah, from all these calls you are going to get order n added to itself n log n times. So, sorry, log n up to the base 2 times order n. So because n is 2 to the power t, there are going to be t number of terms in here, okay, until you get 1. Yeah. So yeah, if that is not clear, just think about it a bit, or take some power of n and do this expansion. So we can do it for 8, for example. So yeah, let me not do that because it is already 12 past 20. But yeah, you can convince yourself from whatever I said that this is indeed n log n complex. Yeah. So this explanation, yeah, this algorithm is taken from Golub and Manzone's book. Okay. So I can also upload it in our set of books, or you can download it from DigGen. So I can upload it today. I will upload it for you. Alright, so that is basically FFT. More or less, we are through now. Yes, and if you do this further expansion yeah, of F4, then you get these structured matrices like that. So yeah, you can see this matrix factorization of this Fourier matrix. We are of course multiplying this with the permutation matrix also at each step. So F times yeah, the first permutation matrix, then there is another permutation matrix like that, and this expression we are writing as yeah, these matrix factor, and these are all sparse matrices, all diagonal, so block diagonal. This is 4 cross 4 identity matrix. This is another diagonal matrix, yeah, and so on. So yes, you write your Fourier matrix as a product of these nice structured matrices, and yes, exploiting this structure for matrix vector multiplication, is what beneath the FFT is the, yeah, it is what behind beneath the FFT trick. Okay. So this matrix factorization can also be exploited in some other matrix algorithms. Okay, so if your problem involves some matrix manipulations and yeah, then if your matrices are of some specific structure, then yeah, in many times uh, these kind of matrix factorizations are exploited in giving faster algorithms. Okay, all right, so you can go through this. So another important application I want to mention is yeah, in image processing. For example, image compression. So there are multiple applications. So one is, for example, polynomial multiplication. So yeah, the coefficients are obtained by convolution of yeah, the coefficients of individual polynomials, and to get those coefficients, you can apply FFT. So that is one. Then discrete PDEs. So if you discretize your PDEs and yeah, want to solve PDEs using discretization, then yeah, you have you are basically solving system of linear equations, something like this. And yeah, again, you can exploit FFT structure in your underlying matrix. And yeah, another application is image compression. So yeah, everyone does it actually daily. So our JPEG is actually uses this FFT algorithm. So yeah, the idea is as follows. So if you have a sine wave, for example, and if you want to store this in time domain, then you need infinitely many components or coefficients, right? For each time instant, you need to know what is the value of this function to store this. Okay. But if you take its Fourier transform, then yeah, you have just one frequency component, so it's enough to know just the fundamental frequency. Okay, so using Fourier coefficients, yeah, you can store your signals very efficiently. Not always, but in some cases at least. Yeah. So you have your time domain vector here, and this is the DFT of that. So these are the transform coefficients. These are time domain coefficients. So these are all non-zero, let's say. Okay. And there will be cases where here you get sparse coefficients. So most of them are zero. Only specific coefficients are non-zero. Okay. So you can go from here to here by taking FFT and log n, and then you can uh, store your data much more efficiently just by using this sparse coefficient. You need not store this zero coefficient. Okay, so that is uh, one one possible situation where your compression is coming from. So you are storing your data exactly, yeah, without losing any information. So of course, while discretization, you have lost some information, but after that, yeah, you are using that. You are storing your information, yeah, retaining all coefficients. Okay. So there are also compressions using what is called as lossy compression. So there will be situations where you have non-zero entries, but even if they are very close to zero, even if you throw them away, yeah, uh, visually you will not see any distortion. Okay, and that's what JPEG exploits. Okay, so you take FFT in n log n, and coefficients which are close to zero, you throw those coefficients also, and only keep the significant coefficient. So this is lossy compression, but it still gives very good reconstruction. Okay, so this is what JPEG exploits. Yeah. When you take image, it's FFT or wavelet or whatever, discrete cosine transform is obtained, and then yeah, many coefficients are just thrown out. Okay. You are not compromising too much on your quality of your signal, even if you throw those coefficients away. Okay. So that is another application. Okay, so that is that. And yes, I have also given some links here which you can have a look at later on. Okay, so let me just show that. Alright, so you can also check out this other links for more sources. So there are some online video lectures and some videos. And apart from that, yeah, just give me a moment. It's taking time to load. Yeah, so you can check out this website if you are interested. Okay. Yeah, it's taking a bit long to load. Bit low. Okay, it's not working, but yeah, you can check this later. Okay, and I've also uploaded some recent material, so some recent literature on this. So you can check that also. Okay, so some recent papers. So of course, yeah, only for those who are interested. Okay, so there is what is called as a graph Fourier transform, and there are approximate graph Fourier transforms, and these some of these papers give some idea of recent happenings in that area. So those interested can have a look at this. yeah, and this is one group which I found which works on both software and hardware aspects of FFT. Okay, so I'm unable to access some of these links from the KGP server. So yeah, from outside you can see if you can access some of these things. Okay. So yeah, those who are interested, yeah, they can check these things out also. So some recent, I mean not very recent, but yeah, I don't know how old these things are, but up to 2014 at least, yeah, you can see the development in this area. Okay, so that is just for your information. Okay, so coming back. All right, so that's all I wanted to say regarding SFT. So, yeah, now we can start Laplace transforms, and yeah, if there are questions or comments, yeah, feel free to say your comments or anything. Okay, so let us start with Laplace transform now. So yeah, this is not going to be too difficult. I think if you have followed Fourier transform, then yeah, you are going to understand everything. So yeah, this week is not going to be too difficult to understand. Like some subtleties, but yeah, not too difficult. Okay, so let's give the definition of the Laplace transform. So this is the definition. So far we were dealing with these complex exponentials with zero real part. Okay, so everywhere yeah, we had just the purely imaginary component. Yeah, so our complex exponential had no real part so far, and that is going to change now. We are going to incorporate real parts also in the complex exponential. So like I said last week, these set of vectors, they don't form orthogonal set of orthogonal set of functions, but they are still independent. Okay, so uniqueness and all is still there, but orthogonality is lost. Okay, so Parseval's theorem, for example, will not hold. So norm of xt squared is not same as norm of x squared and so on. Okay, integral is again from minus infinity to infinity. So we will encounter the other type of Laplace transform also. So this is called two-sided Laplace transform. One-sided Laplace transform has integral from 0 to infinity. That is for causal signals, okay, which we will come back to later on. Okay. So S is sigma plus j omega. For Fourier transforms, we had sigma equal to 0. Yeah. Again, we are going to have convergence issues. So for this Laplace transform to exist, this integral must converge. Okay. So we need to understand when the integral will converge. So that is related to region of convergence of the complex plane and so on, which we will come to soon. Okay. So this integral may not be convergent everywhere of the complex plane. So for all values of S, the integral need not converge. It may converge for some specific signals, but yeah, for arbitrary signals, you may not get convergence for all values of S. And yeah, those regions of the complex plane where we do get convergence, yeah, we need to identify that region, and that region is called region of convergence. Okay, so yeah, we will explain all those. Okay, so let us try to understand this definition from the Fourier transform perspective. So let's rewrite this complex exponential by separating the real and imaginary part like this. Okay, so let's consume this real part with our signal. Yeah. So The Laplace transform is just the Fourier transform of this complex signal. So I hope that is. And we know how to find the inverse Fourier transform for any signal. So let's apply the same formula in here. So this is our time domain signal, and this is its Fourier transform. And now how to obtain this time domain signal from its Fourier transform? That is by this formula. You just do this integral for the Fourier transform, and then 1 over 2 pi factor. Okay, so this is which is straightforward. And now we can take this exponential to this side. This integral is independent of t. Sigma is constant. So we can take this inside the integral and nothing changes. Okay. So x of t is this expression which follows from this simplification. And now we can back substitute for sigma plus j omega. Okay, so this is S, and this is the inverse Laplace transform expression. Okay. All right, so from where this j comes from, that we need to understand. Okay, so there was no j here. So any ideas, anyone, from where that j comes from? The limits of integration have also changed. So here it was minus infinity to plus infinity. So up to this point, everything follows from Fourier transform, and there is a slight change in here.
Variable omega is converted to
Right, exactly. So here the variable of integration was omega, and omega varies from minus infinity to plus infinity. Sigma was fixed. Okay. So S. I think you can do that simplification. Okay. Let me not spend too much time on that. S is sigma plus j omega, and omega goes from minus infinity to plus infinity. Okay, so you do this change of variable, and I will look at this comment in a moment. That's where this limit comes from, going from d omega to ds. There is this 1 over j factor, and this is the inverse Laplace formula. Okay, so the thing to notice is yes, the integral for Laplace transform must converge. Okay, so the set of points where this integral converges, that is called the region of convergence, ROC. Region of convergence. Okay, so set of complex numbers where this integral converges. Okay, so sigma must belong to the region of convergence. Okay, if it does not, then all of this does not make sense, because if sigma plus j omega does not belong to the region of convergence, then integral won't converge. So sigma must belong to, of course, plus j omega also, but this is in the region of convergence. So we'll take one example also to understand region of convergence better, but just hold on to that for a moment. Okay, so while taking this inverse Laplace transform, this quantity sigma which we fixed, okay, omega we varied from minus infinity to plus infinity, but sigma was fixed, and this must be in the region of convergence. Okay, so we'll do one example of a complex real exponential. So x of t is equal to e to the power minus 80, and we will find explicitly the region of convergence for that, so that you will get a better idea. So the thing to make note of is while taking inverse Laplace transform, uh, you must take the inverse Laplace transform within the region of convergence. Okay, so this sigma. So let me give you one figure. So region of convergence. Okay, so just let me take this for granted for now, and we will show why this is true. So A, I'm showing the region of convergence for this signal. It is causal and A is positive. We will derive this why this is true. Okay, but yeah, just let's take this for granted for now. So this is minus A, and this is the region of convergence. Okay, for this this function. So this is the region in the complex plane. All complex numbers having real part greater than minus a is where this integral converges. Yeah. So only for this specific function. Sorry. Only for this specific function. In this region, its Laplace transform converges. So while taking the inverse Laplace transform, this integral, okay, so you are fixing some sigma within your region of convergence. So that could be anywhere, okay. Does not matter whether you take, for example, this sigma and do the integration over this vertical line, or you do it over this line. It does not matter as long as sigma is within the region of convergence. Okay. You will get back the time domain signal by taking any sigma, provided it is within the region of convergence. So yeah, we will understand this better in a moment. So let me look at the question. Yeah, right. So this is correct. All right. So where was I? All right. So uh, let's uh, let's see an example to find the Laplace transform and the inverse Laplace transform as well. Okay. So we have our familiar example of the complex exponential. Yeah, here it is. And yeah, you can just apply definition. Okay, so since there is ut in here, you integrate it from 0 to infinity, e to the power minus at, and there is e to the power minus xt. So this is s plus a. Okay, sorry. And now if you evaluate this, this is just 1 over s plus a. Not everywhere. We will soon come to the region of convergence. But yeah, let's not worry about that for the time being. Okay. So this is straightforward. Okay. This vanishes at infinity, provided that the real part of this is positive. Okay. So t is varying from 0 to infinity. So the Laplace transform vanishes at infinity, provided that the real part of s plus a is positive. Right? If the real part of s plus a is negative, then at t is equal to plus infinity, because of its negative sign, the integral is going to diverge. Okay. So you can see now from where this ROC comes from. Yeah. I also have that somewhere here. So yeah, ROC is the subset of the complex plane where the integral converges. And yeah, the real part of s plus a must be greater than 0 for this integral to converge at infinity. Okay. If it is negative or 0, then yeah, this may diverge. Okay, so This is our region of convergence. If real part of s plus a is strictly positive, then the integral is going to converge, and that is our region of convergence, ROC. Okay. So I hope everyone gets from where this region of convergence comes from. Okay, for a positive, yeah. And for a negative, even if you take non-causal signals, yeah, everything boils down to uh, figuring out when this this integration will decay. Okay, so if you have anti-causal signals, then t is going to go from 0 to minus infinity, and in that case, yeah, you need to figure out this sign properly. Okay, so that the integral converges. So yeah, I do make mistakes in those cases, but and some of you also might make mistakes, but yeah, that is where you have to be a little careful and figure out what is the ROC for your underlying signal. But if you understand, yeah, from where ROC comes from, you should be able to figure out for any signal what is the ROC. We we don't want this quantity to blow up. Okay? We want this to converge to zero, so that we don't have any trouble evaluating this integrals at plus or minus infinity. And since we are dealing with exponential signals, uh, yes, exponential signals either decay at plus infinity or minus infinity, one of those two. If you have decaying exponential for t positive, then something like this, then yeah, they become unbounded for t equal to minus infinity. And if you have a growing exponential thing here, then yeah, they decay at t is equal to minus infinity. Yeah. So those things you have to be a little careful while determining this ROC. Okay. So I hope the forward direction is clear. Yeah. Why the Fourier transform of sorry, the Laplace transform of the complex exponential is 1 over s plus a. Yeah. The inverse one also we are going to do, and yeah, we are going to take it. Yeah. Damn you, you are not saying anything. Yeah. So as I was saying, yeah, we are going to refer to our Fourier inverse Fourier integral. Okay, we are going to take a shortcut, but there are two ways to evaluate the inverse Laplace transform. Okay. So one thing is okay. One approach is to do the complex integration. Okay, so that is if you have done complex analysis, then suppose you are in ROC, and let's take suppose sigma is equal to 0 is within your ROC, for example. Then yeah, you want to do your integration over this line. Okay, omega goes from minus infinity to plus infinity, and if you have a rational function with numerator degree strictly less than the denominator degree, in that case, yeah, there is this trick. So yeah, I will not get into details of that because it will just take a lot of time to explain these things. You can take this infinite contour. Okay, so this radius is tending to infinity. Okay, and to evaluate this real integration, where omega goes from minus infinity to plus infinity, you can instead evaluate this contour integration. So you can show that yeah, the contour integration and this real integration are the same. That follows because the integration over yeah, this semicircle vanishes when the degree of the numerator is strictly less than the degree of the denominator. So that is one way, okay, using complex analysis. And for this contour, you can refer to Cauchy's integral formula and residue theorem and those kind of things uh, to find the inverse Laplace transform. So that is one way to evaluate that. But we are not going to take that approach. We will use this Fourier transform integral, okay, to evaluate the inverse Laplace transform. Okay. So later on, if we have time, yeah, I might explain this, but I don't think we are going to have time to go through this. So let me show you quickly how the inverse Laplace transform follows from the inverse Fourier transform. Okay. So our ROC includes the purely imaginary axis. Okay, because the ROC is given by the region of the complex plane, which is strictly greater than minus a. So this is the part where sigma is equal to 0, which is included in the ROC. So I can perform this integral, yeah, over the purely imaginary axis. Okay, taking sigma is equal to 0. No one stops me from doing that because sigma is equal to 0 is in ROC. And now you are just reduced to the inverse Fourier transform integral. We have already evaluated. So this is just e to the power minus 18. Okay. So you have this Laplace pair e to the power minus 80 ut and 1 over s plus a. Yeah. And now you can use this same trick to find the pairs for any Laplace pairs for any exponential signal. Okay. So for sines and cosines, you can sine of t ut and cos of t u of t. Okay, so you can write these two using complex exponential and use their Laplace transforms to find Laplace transforms of these signals. Okay, so for any rational function now which is proper, e of s over q of s, you can find the inverse Laplace transform. Yeah. Just do partial fractions to separate this rational function, and you already know the Laplace pair. 1 over s plus a is paired with e to the power minus a. Okay, so I hope that is fine. So let us do these simple cases also quickly. So for unit step signal, yeah, you can put in a is equal to 0 in here. Okay, so for unit step, for example, we have this integral 0 to infinity e to the power minus d. And this integral converges if real part of s is strictly greater than 0. Yeah, that's what you need for this complex exponential to die at infinity. Okay, if it does not die, then yeah, the integral is going to be infinite. If it is 0, for example, you are going to get a constant, and constant of integration of constant from 0 to infinity is infinity. Okay, so r real part of s must be strictly greater than 0 for this integral to converge, and the Laplace transform will be 1 over s. So that is straightforward. You can also do Laplace transform for Dirac delta. Yeah. So just by definition, yeah, so yeah, if x of t is delta t, then once you evaluate this integration, that is just Yeah, you evaluate this at t is equal to 0, which is 1. Okay. So x of s is 1 everywhere. Yeah. No matter what s you take, you always get 1. Yeah. So that means the region of convergence is the entire complex plane. Okay. Because the integral converges everywhere. No matter what s you take, x of s is always 1. Any questions on that? Okay. So let me do maybe a couple of, at least one case before we end today's class. So properties, yeah, I'm not going to rederive all the derivations, okay? It just follows by using same ideas which we used in Fourier transform. Same manipulations more or less, just a couple of cases where you need slightly different arguments. Only those I will discuss. And we need to understand the ROC properties, which is slightly different in Laplace transform. So yeah, in Fourier transforms, we did not have any ROC cases as such. So for those properties, we also need to figure out what is the region of convergence, okay, for delays, multiplication, convolution properties, linearity properties, etc. Okay, so those things I will discuss in brief, but yeah, these derivations, we will not do them again and again, okay. I hope you can do it as an easy exercise. Final value theorem, initial value theorem, yeah, these things I will discuss, which is different. Differentiation and time also involve slightly different arguments. So yeah, those things I will discuss. Okay. So let us understand maybe one more case for this ROC. Okay, so yeah, everyone be careful. Okay, so just don't take my argument for granted. You also convince yourself, and yeah, if I make any mistakes, yeah, you correct me, or yeah, just do those necessary corrections. Okay, yeah, I do make mistakes while doing this things. Okay, so yeah, be careful while reading these things. So we took this case where the real part, I mean, this was the real number, which was positive. And now let's look at the case where it is negative. The signal is still causal, but yeah, A is negative now. So we have an exponentially growing signal. Okay. So something like this. Starts from 1 and goes to infinity. So in Fourier transform, yeah, we could not find Fourier transform of this because it is not integrable. Yeah, if you just multiply by e to the power j omega t, this is not an integrable function. Neither L2 nor, sorry, not neither square integrable nor absolutely integrable. But in Laplace transform, yes, you can still integrate it for by choosing S carefully. Okay, so let's go through that. How to make this integral convergent. Yeah. So you choose those complex numbers which decay faster than yeah, this grows, okay, and somehow you make the integration go to 0. That is the idea which yeah, I think everyone knows. Okay, so when we write this out, so let's put b is equal to minus a, and b is positive now because a was negative. Okay, so we can write this uh, formula as this exponential e to the power minus in bracket s minus b. So minus minus becomes plus. So we have minus s and plus b, and plus b is minus s. So this is correct. And we want real part of s minus b to be positive. Okay, strictly positive. That will ensure that this exponential will decay. Integration of this exponential will go to 0 at infinity. Okay, so this is our condition for ROC. Real part of S minus B should be strictly positive, and that means real part of S should be strictly bigger than B. Okay, and B is minus A. Okay, so that is our ROC. Real part of S must be strictly greater than minus A. Okay, so pictorially, yeah, A was negative to start with, so minus A must be positive. Yeah. So that's why ROC looks like this. Okay. Minus A is positive, and everything to the right of this vertical line is where the ROC is for this signal. Okay, so I think this is correct. Okay, I think I have not made a mistake in this, but yeah, please check for yourselves also. Okay, so I think we can end here. Tomorrow I will discuss some more cases of yeah, these situations where you have anticausal and A positive, A negative, both sided, etc. Okay. And we will also look at some more ROC properties and yeah, Laplace transform properties, etc. Okay. So I think that's it. Thank you all for wait.
Excuse me, sir.
Yeah, yeah. If there are questions, I am here. But those who want to leave can leave.
Sir, can you please upload this handwritten PDF?
Yes, yes. I will upload it right now after this class. Okay.
Okay, sir.
So it, here in the notes section itself, I have made another folder handwritten, and there I will put it. Okay. So let me stop recording and I'm waiting.